Hey guys, so we are on 3.2. This is day 1, differentiability. So we've come across a bunch of different things. We've taken derivatives. We've had problems where the limits don't exist, that type of thing. We've been looking at derivative graphs and what those look like, and that all, derivatives have to do with slopes. But we have to remember for a function to be differentiable, it must be continuous. And so if we have a graph or a function and we know that it's not continuous, then automatically we know that it's not differentiable. Okay, so we have 4 cases in which the derivative fails to exist. Okay. First case, we have a corner. A corner just is like with an absolute value. This is an absolute value graph. And on this graph, we do have a little corner right here. What happens is that when we go to take a derivative, the slope of the tangent line on the left of that graph is a slope of -1. But the slope of the tangent line on the right of the graph is a slope of +1. So what happens is when we have the limit as x approaches 0 from the left of f prime of x, the derivative, equals -1, this differs from the limit as x approaches 0 from the right of f prime of x, the derivative, because it's going to equal 1. So since these are not the same, since these derivatives or these limits are not equal, and these are the limits of the derivative graph, since they're not meeting at the same spot, we have a discontinuity. So it's going to be a different derivative, so we're not going to have a derivative for this type of problem. Okay, it needs to be in agreement, it needs to meet at the same place on the left and the right. Okay, so anytime from now on you see an absolute value or you see a graph that has a corner like that. There's also a graph that would have a corner is like if you had a straight line on one part and then all of a sudden it curves off. That would be considered a corner as well. Any little straight peak like that, a straight peak. Okay, where there's like an edge because it's edgy. All right, next graph where the derivative is going to fail to exist is with something called a cusp. So that's because if we were to have a tangent line right here and right here, the slopes of this are decreasing, not at a constant rate like this one was, because that's a straight line. This is curving. So it's decreasing, 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 decreasing to infinity for the derivative. And then on this side, it's decreasing, decreasing to infinity going this way. But if we think about it, the tangent line from left to right is positive. So it's increasing, increasing, increasing. Okay, so because it's going to infinity from both sides, I was about to use my highlighter to write that, we can have the limit as x approaches 0 from the left and the right of the derivative of f of x. It's either going to go to positive or negative infinity. On the left, it has a negative slope, so it would be going down to negative infinity. On the right, since it has a positive slope, the derivative would be going up to positive infinity. Okay. It's not a constant increase because it's not linear. All right. Okay, so these are the 2 cases so far. Third case is if we have a vertical tangent. So this, normally, we've been dealing with the cubic where it's facing upright. When it's sideways like that, it's a cube root function. And what happens is we have a tangent line on that shelf. Remember the shelf? But that tangent line is a vertical line. And vertical lines have an undefined slope. So that just means that the limit as x approaches 0 from the left and from the right of the derivative of x is going to go to plus or minus infinity, just like the cusp one did. So anytime we see a cube root function like that, where there's a shelf or a vertical line tangent, the slope of a vertical line is undefined. So anytime you have a vertical line and you're trying to find the tangent line, it's no bueno, it's not going to work, so it's not going to have a derivative. It's going to fail to exist. For that next one, this one's kind of obvious. We have a discontinuity. It's where one or both sided derivatives will be non-existent. And obviously we know that this is a jump. Jump, jump. So we know that the limit does not exist for a jump. Limit DNE does not exist. So because of that, this isn't continuous. So I can even go about it that way. I can be like, okay, this one isn't continuous, so since it must be continuous to be differentiable, this one automatically is not differentiable. This one is continuous, but it still has a derivative that fails to exist because it's a cusp. This one is continuous. There's no jumps, holes, breaks, gaps, anything, but it's not differentiable because of this corner. It has one-sided derivatives that are different from each other. And then this one, it is continuous. It flows nicely. It doesn't have a hole, jump, break, gap, nothing. But it has a tangent line to the graph, and that would make the slope undefined, and that doesn't work for us. We can't have 0 in the denominator, so the limit doesn't exist there either, because as we approach 0 from the left and from the right, one side is going to positive infinity, the other one is going down to negative infinity. Okay? So in your homework, it's in the book pages, you're going to be dealing with mostly the graphs. So let's go ahead and look at D. We're going to find all points in the domain of F where it is not differentiable. State why it is not differentiable at each point. Okay, so looking at letter D, so I want to start there. We have a graph, and I see that we've got a corner right here. And then at x equals 0, there's 2 points, so we've got a jump going on right there. And then when x is 3, we have a hole. So f of x is not going to be differentiable because of those 3 problems. So this is not continuous, first of all. So we can say, but it is continuous in certain spots. So like between -2 and -1, from here to here, it's continuous. From here to here, it's continuous. From here to here, it's continuous. And from here to here, it's continuous. So there are parts of it that will work, but not all of it. So we can say f of x is differentiable everywhere except x equals -1, because the limit as x approaches -1 from the left of f prime of x will not equal the limit as x approaches -1 from the right of f prime of x, just like our little definition for the corner graph, except x equals -1, comma, x equals 0. That's where our jump is. So when we have a jump, so because limit is blah, blah, x equals 0, because it isn't continuous there, comma, and the last one is x equals 3, because there is a removable discontinuity there. Okay, So we just have to make sure that our write-ups are complete, that we've touched on everything. It's very thorough. I don't want books for these write-ups, but I definitely want it to be thorough. It's better to have too much rather than too little. That's a for sure thing. Okay, let's try another one. Let's do letter A. Or no, let's do letter B. Letter B. So f of x equals, it's a piecewise function, x squared over 2, where x is greater than or equal to 2, and x, where x is less than 2. So first of all, let's see if this is continuous. So to see if it's continuous, that means when we plug in a 2 for both pieces of this function, we should get the same value. So let's try f of 2 for the x squared over 2, so 2 squared over 2. 2 squared is 4, 4 over 2 is 2. And if I plug in a 2 into the other piece, you're just replacing the x with a 2. So it is continuous. Okay, well now let's check the derivatives. Are the derivatives continuous? So let's try f prime of 2. Now f prime would be, we would drop the exponents. That would be a 2x over 2. The 2's would cancel, so I would just have x. When you plug in a 2 for x, you just get 2. For the other one, the other piece, the derivative of x is just 1. And we can't plug in anything because there's no variable. It's all gone. But definitely, these are not equal. Okay, so the derivatives are not going to have, there's not going to be a derivative there because they're not going to meet. They're not going to be in agreement. Okay, so we can say f of x is differentiable everywhere except, are you done, Lucas?
Yeah.
Okay. Everywhere except except at x equals 2. Because the limit as x approaches 2 from the left of f prime of x does not equal the limit as x approaches 2 from the right of f prime of x. So the key to these now is, now that we know derivatives, we have to look at the derivatives to see if it will fail to exist. Okay, so I'll skip the other two because they're pretty straightforward. And let's go ahead and look on the next page, if I can get there. We'll do letter E. That's a good one. So letter E, we have a graph, just like you'll see in your homework. And I already can tell that we're going to have a problem here and here. Why am I going to have a problem there? Well, those are corners. So I know it's not going to be differentiable at those points. So let's see, what points are those? 1, 2, 3, 4. So this is a -2, and this is a +2. Okay, those are corners. So I know that because the slopes are going to differ there, that their limits of the derivative are not going to be in agreement. So it's going to fail right there. Okay, so I can say, but everywhere else it's continuous, and everywhere else it'll work, just not at the corners. So we can say f of x is differentiable everywhere except at x equals -2 and +2. So I'm going to put plus or minus 2 because we always have to say why. The limit as x approaches -2 from the right of f prime of x, I'll start on the right, I guess, does not equal the limit as x approaches -2 from the left of f prime of x, and the limit as x approaches +2 from the right of f prime of x does not equal the limit as x approaches 2 from the left of f prime of x. period. Okay, so those are my write-ups. All right, so this says a lot of things, and we're gonna just go ahead and get to the meat of it. Okay, so you're gonna need your graphing calculator, and we're gonna be calculating derivatives with our graphing calculator, so I want you guys to write this down. Now, it does depend on what kind of graphing calculator you're using, so hopefully you got one like mine, the TI-84, either the older model or this one. You know, this one's nice because everything's in color. I like that. And we're going to use our calculator to calculate derivatives. Didn't think you could do that, huh? Isn't that cool? We're going to learn how to calculate derivatives on our calculator. Okay. The keys to get there are pretty standard. So even if you don't have a TI-84, it should still work. Oh, hold on, let me clear what I have in here. Okay, so it should still work no matter what. The keys that you're gonna need the most for this are the math button and the 8 button. Okay, so in a calculator like mine, when I hit math and then the number 8, it puts in my derivative like this. Okay, it's where I have d over d in a box, parentheses, a box, then this vertical line, and then box equals box. Okay, pretty much what goes in those boxes, it's always d dx, and it'll always be x equals something. The function is what goes in these parentheses, and the specific value that we're finding it at goes here. When you're not looking for a specific value, you just want in general, then you just put an x there. And we'll go over that today. If you have an older model, when you hit math 8, it might say n for n derivative. I have no idea why it's called that. It's just how it is. And it's gonna look like this. So you would type in f of x, that's the function. And then x is always x, but then the second x, this is your specific value. So if you want it in general, then you keep it in x. But if you want, like when x equals 2, you would plug in a 2 right there. So it just depends on the type of model that you have, but you can totally use your calculator when you're allowed to use your calculator, because half the time on the AP test, you're gonna be able to use the calculator and half time you won't. So you need to be able to do both. And it is kind of nice to be able to check your work. All right, so for this next example, we're gonna compute the derivative of x cubed at the specific value of 2. So you're gonna see it in that notation sometimes, because we're using the book uses the old notation. And basically that's the derivative of x cubed at x equals 2 using our calculator and then confirming it by hand. So in the calculator, I need to change that. I already have it ready to go, so I'm going to type in the x for d dx. The function is x cubed. So I have an x, and I got to raise it to the 3rd power. And then it's at that specific value of x equals 2. So I want to write down what you're seeing in the calculator. It should be d dx of x cubed at x equals 2. Okay, and we are going to do it by hand also, but when I hit enter, this is what I get, 12.000001. Okay, now let's do it by hand, make sure we get the same thing. So by hand, when we take the derivative of x cubed, we know that we drop the exponent and we take it down a degree, so 3x squared. But at that specific value of 2 means that we have to plug in a 2 for x. 2 squared is 4. 4 times 3 is, oh my gosh, 12. Woohoo! Okay, so what about the 0.000001, Mrs. Garcia? I'm like, well, we're using a calculator. So the calculator starts messing up after the 5th decimal place. So down there at the bottom, it says, it turns out that the ender is accurate up to 5 decimal places. Anywhere after that, it is not accurate. I also have some other bad news for you guys. Turn the page. Look, it even says bad news. So the bad news is sometimes ender gives you the wrong answer. Yeah, I'm sorry, but sometimes the calculator just doesn't know. It thinks it knows, but it doesn't. So it's not anything you're doing wrong. It's just the calculator thinks that it knows what's happening, but it doesn't. Okay, so let's take a look at this. So we're gonna use our graphing calculator to compute this. We're taking the derivative of the absolute value of x. So it should look like this, and I'll show you how to type that in your calculator at the specific value x equals 0. Okay, so we're taking the derivative of the absolute value of x, but keep in mind something. We already learned absolute value is like this graph. It's going to have a corner. So the derivative is going to fail to exist at 0. So we already know that going in. The limit fails to exist there. So let's see what the calculator tells us. So I'm going to hit math 8. This is always an x, so d dx, and it's of the absolute value. So to get to absolute value, you have to hit math, scroll to the right to num, N-U-M, for number, and then that very first one, ABS, is not the abs on your stomach. It's talking about the absolute value. And there it is. And type in an x. And oops, and it's at x equals 0. And I'm going to hit enter. And look what it says. It says that the derivative is 0 at that point. Okay. Well, what is the derivative of it actually? Because it's not 0. So if we look at it on the graph, which we know what it's going to look like, so you already know pretty much what the answer is. On the graph, it's an absolute value. So it has a corner at 0. So the limit does not exist. So it's not differentiable there. Okay? So what do we do then? Well, when you know, like, it's an absolute value, it's going to have a corner, the derivative is going to fail to exist. So that means that you know that it's not going to have a derivative there. Okay? So what you have to do is you need to rely on your own common sense. Okay? So if you know a graph isn't continuous, it's not going to have a derivative. If you know that the graph is continuous, but it has a corner or a cusp or a vertical tangent line or it has a jump discontinuity, then you know that it's not going to have a derivative at that point where that happens. So you have to be able to rely on your own knowledge of that, okay? So we just got to be careful about it. So we can use the ender to compute derivatives at a point for us, but we just have to make sure that we know that the function is differentiable at that point. So we really do have to pay attention to those things, because if we just heavily rely on the calculator, it will steer us wrong. Remember, we are the humans. We are smarter than the calculator. The calculator is a machine. It is not smarter than us. We have common sense. A computer does not. Okay. So we're going to use the ender to graph the derivatives of the functions below and make a guess as to what the derivative is based off the shape of the graph. So let's go ahead and start with C, since we know what that looks like. F of x equals the absolute value of x. So we know that we already know what its graph is going to look like. Absolute value, okay? And so this is f of x, which leads us to the derivative graph, okay? And I need a 1 and a -1. and a 1 and a negative 1. So we know based off of the absolute value that on the left it's going to have a slope of negative 1. So from the left coming to 0, it has a slope of negative 1. So from here forever to the left. And then from 0 going to the right, it has a slope of positive 1. So from here going forever. And there is our f prime of x, our derivative graph. All right, so make a guess as to what the derivative is based off of the shape of the graph. So the derivative is going to be f prime of x equals, well, the derivative graph is, well, we have negative 1, and that's for x's that are less than 0. That'll work there. And then from positive 1, x's greater than 0 will work there. We just have to not include that point. So that's why I don't have the or equal to bar. So this will be the derivative that will work for that function. Okay. All right, let's try another one. And this time we're going to use our graphing calculator. So let's try B. So in our graphing calculator, I'm going to show you some things. We're going to type in the original function. We're going to call the original y1, and the original is sine of x. We're going to call y2 the derivative. So we're going to need to take a d dx of y1, and we want it in general. So x is just going to equal x, just to see in general what it is. Okay. All right, so turn this on, have y equals. So I need the sine of x, that's my original. And then for y2, I need d dx, so I hit math 8, remember? D dx of the derivative of sine x. So I'm just going to type in sine x because I don't know how to input y1. I think there was a way, but I don't remember. Anyways, so I'm just going to put sine x, because we're going to take the derivative of that, and x equals x. All right, and I'm going to graph. There's sine. Here's the derivative. And it makes sense. We know that we know what the sine wave looks like, and we know that from the last lesson that the derivative of sine is cosine. So the red graph there is my cosine graph. Okay, so we know what sine looks like. F prime of x, we'll just graph it. We know what cosine looks like, but we'll graph it since we're focusing on the derivative of this. So cosine starts off up at 1, and it goes bloop, bloop, bloop. I'm just going to kind of fake it. Bloop, bloop, bloop. There's cosine of x. So since we know this one, it's kind of easy to figure it out. The derivative function would be f prime of x equals the cosine of x. And we knew that. Okay. Let's go ahead and look at letter A, just because this one we might not know off the bat. So in your GC in the graphing calculator, you're going to have a y1 equals the natural log of x plus 1, and y2 is going to be the derivative, d dx, of y1 at x equals x. Okay, so I'm going to go back to my calculator. Oops, you guys couldn't see that, sorry. Clear out what I have in there. For y1, I'm going to have the natural log of x plus 1. And then for y2, I need the derivative. So math 8, so d dx of the natural log of x plus 1, because it's going to calculate that derivative for me at x equals x, because I want it to be in general. And I'm going to hit graph. So there's natural log of x. There's the derivative. Okay, so let's draw these. So So let's start with, I'll try to squeeze it in there. Looks like, the blue graph is my original. It looks like I have a vertical asymptote at -1, x equals -1. So I'll put that in there, and I'll use a different color. And it looks like I'm going through the origin, and I'm going, no, it looks good. Okay, so this is f of x. And then for f prime of x, the derivative, looks like the red graph is my derivative. Looks like I also have a vertical asymptote at the same spot, x equals -1. But this one, it looks like it's going through 0, 1, and it goes a little bit differently. So let me use a different color. It's doing that. This is f prime of x. So what is the derivative function? So we have to make a guess. Well, we have seen functions like this in Math 3 last year. So let me write derivative. And since we're having this like little, it looks like a rational graph. It makes me think of 1 over x. So I'm gonna make some conjectures. So I'm gonna try out 1 over x. I'm gonna go to y equals. I'm gonna go to the third line down, and I'm gonna put 1 divided by x and see what happens. Okay, so I definitely don't want this left-hand side of the graph, so I'm gonna have to restrict the domain. But this right-hand side, it's so close to the red, I just need to shift it over 1, I think. So to shift it over 1, I need to divide by an x plus 1. So I'm gonna go back. Instead of 1 over x, I'm going to put parentheses. You need to put parentheses. X plus 1. And now let's see what happens. There's the original. There's the derivative. It's slow. Here comes 1 over 1 plus x. Oh, look, and the black covered up the red completely. So I just need to ignore this side, so I have to restrict the domain. So I want everything bigger than -1 on the x. Okay, so 1 over x plus 1 was a good guess. Looks pretty exact, and it's got to be where x is greater than -1. Okay. All right. Again, I want to reiterate that when you're looking for a derivative, the function has to be continuous in order to have a derivative. So if it's not continuous right off the bat, it's not going to have a derivative. So it's good to know that from the get-go, from the beginning. So if you're asked to find the derivative of like an absolute value, you're like, oh, wait a minute, I know that has a corner. It's not going to work. It's not going to have a derivative at that point. Okay. All right. So remember something that is continuous. That means it has no points of discontinuity. It has no jumps, holes, breaks, gaps, nothing. No asymptotes. Okay. Here's this theorem. It says differentiability implies continuity. So what we can say is if f has a derivative at x equals a at some x value, then f is continuous at x equals a, that x value. Is the converse true? Well, the converse would be on the flip side. If f is continuous at x equals a, then is f also differentiable there? Is that converse going to be true? If it's continuous, is it automatically going to be differentiable at that point? Well, we have 4 cases at the beginning of this lesson, 3 of which were continuous. It's continuous when we have a corner, but the derivative fails there. It's continuous at a cusp, but the derivative fails there. It's continuous for a cube root function, but because of that vertical tangent line, the derivative fails to exist there. And then, of course, this one is not continuous, so automatically it's not going to have a derivative there. Okay, so if a function is continuous, that doesn't mean that it's automatically going to have a derivative. If it has a derivative at that point, then yeah, we can assume it's continuous because it's got to be continuous to have a derivative. But if it's a continuous function, that doesn't automatically mean that it's going to have a derivative. So I'm going to say nope. And anytime we are saying nope, it's false, we have to give a counter example. So my counter example is going to be the absolute value of x. We've used it a lot today, but it comes in handy. We know that the absolute value is going to fail because it's continuous but has a corner. And we know that because it has a corner, its left and right derivatives are not going to be in agreement. They're not going to be the same. Okay? All right, so that's everything, and I hope you guys have a great day.